I want to introduce you to our tutor, Milica Maricic. She is an assistant professor at the University of Belgrade, Faculty of Organizational Sciences, and she will hold the covariance-based and partial least squares SEM modeling, outline, and applications tutorial. Enjoy.
Okay, so hello, everyone. Good morning for those of you who are maybe just up. So, Anna, thank you very much for the introduction. So, I'm now going to share the presentation I will be using. I also sent the presentation to you, to the technical office. So from my side, I'm completely fine to share the presentation with all the participants. So if you can maybe just tell the participants where they can find it afterwards if they want it, or no, because I'm not sure where they can download it if need.
I will send the presentation here as a text in chat.
Okay, that's great. Thank you.
No problem.
Okay. Okay, so I hope that you can see the slide. I hope everything is fine. So we can slowly start with our today's topic related to covariance-based and partial least squares SEM modeling. So when it comes to our agenda and what we will be going through, at the beginning, we're going to, let's say, briefly introduce what is a SEM model, what a SEM model consists of. And then we will delve a little bit deeper into the analysis itself, where we will focus and try to find and observe the differences between two, let's say, major groups of algorithms, which are used to validate or assess a certain SEM model. So today we will be talking about the two big groups, which are covariance-based and partial least squares SEM models. So we will take some time and observe what are the differences between the two, and how you can actually choose which of those two algorithms to use if you are having a SEM model and you want to assess your SEM model. We will also go through a part related to validation of SEM models, because based on the algorithm we previously chose, there are different approaches. How do we validate a particular SEM model? And of course, at the end, we're going to see how these two algorithms can be applied in R. What are the packages used, as well as the functions used, as well as, let's say, some differences in the R syntax for the two algorithm approaches. So when it comes to SEM as statistical multivariate analysis, first, and how do we describe it in the most easiest way, is that it is a combination of two statistical multivariate analyses. On one side we have factor analysis, and on the other side we have multiple linear regression. So on one side we have factor analysis, which has the goal to group our variables into constructs, new variables. And on the other side, we have multiple linear regression, which allows us to inspect the relationships between our measured or latent variables. So in the next couple of slides, we're just going through the basis of these two analyses, because we need a little understanding on them in order to better understand how SEM is functioning itself. So the first time SEM analysis is mentioned in literature papers is, let's say, more than 90 years ago. However, in the last, let's say, 15 to 10 years, SEM analysis has been vastly used in different scientific fields to validate conceptual models and relationships between variables. So today, SEM is used both in marketing management, human resources management, quality management, and other fields of study. So the analysis itself is vastly is applicable and can be applied in different fields of study. So when it comes to factor analysis, the basic idea of the analysis itself is that some but not all variables can be directly observed. So when we are observing, especially in social sciences, some phenomenon, we are aware that we cannot usually measure them using just one variable. So the most common example is, for example, intelligence or consumer behavior, or so those are some constructs, behaviors, phenomena which cannot be measured solely with one variable or one question. So the basic idea of factor analysis is, in fact, to help us group similar variables which are measured, which we have in our data set, to construct new variables which as such do not exist in our data set. So the idea is to group measured variables, ones we have in our data set, construct a linear combination of our variables and create a new latent variable or factor or construct. Those are all the same, or all synonyms. So factor analysis helps us group our variables and create new latent variables or factors. Why is this pretty handy and pretty useful? It's handy because it helps us reduce the dimensionality of our problem. So if we have, let's say, 100 variables, and we can group our variables to, let's say, 5 or 6 constructs or latent variables, it is way easier for us to manipulate 6 latent variables than to manipulate 100 individual measured variables. Also, factor analysis can also help us see the data more clearly. So some of the keywords that we have from the application of factor analysis, and some of the key results which we are going to need for SEM, is that by using factor analysis, we are reducing the dimensionality of our problem. We are creating new variables, new constructs, and the main benefit is the simplification. It is way easier for us to have less variables to be able to conduct other analysis based on them. So the basic idea of factor analysis is extraction. So what we want to do, we want to extract as much variance as possible from the variables we are observing. Okay, so on the other hand, we said that we have multiple linear regression. So when it comes to multiple linear regression, its basic idea and goal is to help us mathematically model the relationship between our one dependent variable, here marked with epsilon(i), and one or many independent variables which are marked with x. So our idea is to model the relationship between our independent variables and our dependent variable. So the coefficients beta 0, beta 1, beta 2, all the way up to r to beta k are regression parameters. So the parameters which we are usually more interested in are the parameters standing next to our independent variables. So beta 1, beta 2, and all the way down. Why are these coefficients interesting and important for us? Well, they are telling us how a certain independent variable impacts our dependent variable. So based on the sign of our coefficient, whether it is positive or negative, we know the direction of the relationship between our independent and our dependent variable. Also, based on the size of the value of our coefficient, we know the strength of the relationship between our independent and dependent variable. Also, whether a certain coefficient is statistically significant or no tells us whether a certain independent variable has or has not a statistically significant impact on our dependent variable. So the relationship in linear regression is usually stochastic. So we have our stochastic part at the end, or white noise. So when it comes to multiple linear regression, we have certain lists of assumptions which should be valid in a multiple linear regression model. So out of all these 5 assumptions listed here, there is one which is pretty important when conducting SEM analysis, and one should have in mind when creating a certain SEM model. So the particular problematic which can occur in a SEM model is the problem of multicollinearity. As you can see, our assumption here is that there is no multicollinearity among our data. So multicollinearity is a specific problem which occurs only in multiple linear regression. And multicollinearity is in fact a particular situation when there is a strong correlation between our independent variables. So, for example, if the correlation coefficient between our variables x1 and x2 is, for example, greater than 0.9 in absolute values, we would be having a problem of multicollinearity. So when we have a strong correlation between our independent variables, it is a problem. Why? Because we cannot estimate our particular coefficients standing next to each of our independent variables. So if there is a strong multicollinearity in our SEM model, the algorithm itself will going to tell you that the algorithm cannot find an optimal solution. So if there is a problem with multicollinearity, the easiest way to reduce reduce the problem is to remove a certain variable which is highly correlated with other independent variables. So in that sense, exploring the presence of multicollinearity is sometimes suggested or done as a pre-test when conducting and creating a SEM model. So as we said, on one side we have factor analysis, which is going to help us group our variables, and on the other side we have multiple linear regression, which is going to help us find the relationship between our variables, whether those are latent variables or measured variables. It doesn't matter. Okay. Okay. So how does this look for now? So please, if you have any questions, raise your hand, write your question in the chat. Please feel free to interrupt me if I'm going too fast, too slow, or maybe there is something which I haven't mentioned so far. Okay. So after we mentioned our two analyses, before talking about SEM, there are certain aspects of the SEM analysis which we should also talk about. So the first thing is that when it comes to SEM analysis, as an analysis, it's pretty graphic. So whenever you are proposing a certain conceptual model, I can't say that you're obliged, but it's pretty nice and handy to present a graphical interpretation of the model you are actually exploring, testing, and verifying. So when it comes to drawing the model itself, there are certain rules which should be followed. So the first thing is related to how do we present different types of variables on our graphs. So first variables on our graph are measured variables. So measured variables are the variables which we have in our data set. So imagine measured variables as answers to a survey question or measurements that you have conducted. So measured variables are variables which exist as such in your data set as columns, and they are on a particular SEM graph, they are presented in squares. So, for example, observing this small SEM model, we can see that we have 7 measured variables, scale 1, 2, 3, and 4, as well as SAT score, high school GPA, and ACT score. So we can see that these variables are marked in squares, so we know those are measured variables. At the same time, we have latent variables. As we mentioned, latent variables are newly created variables using factor analysis. So latent variables as such do not exist in our data set. So if we would open a data set for this SEM model, we cannot find variables intelligence and academic performance as columns in our data set. So as you can see, latent variables are marked with circles. So in this SEM model, we have 2 latent variables, intelligence and academic performance. And we know intelligence is created as a linear combination of scales 1 to 4. The second latent variable, academic performance, is made as a linear combination of SAT score, high school GPA, and ACT score. So in this part, we are having factor analysis working. So making new variables is the part of factor analysis. What we also see is there is some kind of relationship between our 2 newly created latent variables. So this is the part where linear regression fits in. So linear regression is going to help us explore relationships between our latent variables, and factor analysis is helping us create our new latent variables. So what you can also see on this graph is something which is presented on the graph depending on the software, SEM software you are using. But these errors 1, 2, 3, 4, and all the way up to 7 are easily said some measurement errors. We are going to see a little bit later. These measurement errors can be later used to enhance the model itself. So when it comes to SEM analysis, there are, let's say, 3 main situations how to conduct SEM analysis. So the first one is highly confirmative situation where you as a researcher, you propose a model, you gather your data, you check whether the data fits the model or no. If data fits the model, everything is great. If the data doesn't fit the model, you discard the model and the whole research. So this first approach is completely, it's not common in practice. I mean, why would you discard all your data, all the analysis, all the data and research you've done previously? So the second approach then is to have a few alternative models. This is also an approach happening in practice. So based on your literature review, you generate several different SEM models. And then you collect your data and you test the fit of each of your models to your data. So the model which fits the best, you proclaim that model as your final and the best model. However, the third option and approach is the most common one, and that is model generation. So you start with one SEM model, you try to fit your data to the model, and then you are, let's say, allowed to make small alterations to your model in order to get a better fit. So SEM analysis as such is no magical analysis. So if you are going to conduct SEM analysis, be prepared to redo the analysis quite a number of time, all the way up until you get a model which is, let's say, of a good fit. So model generation, we'll talk about it as well through the presentation. Model generation allows you to maybe remove some measured variables which are not statistically significant, or maybe remove whole constructs or latent variables from the model if they have no impact or on other model elements, and similar. So this slide, this small talk was just to prepare you that SEM model is not a one click analysis, and that you should be prepared to redo the analysis quite a number of times until you get a model which fits the data you have collected. So when it comes to SEM software, as you can see, there is quite a number of software available. So that is also one of the reasons why the analysis is, let's say, quite popular at the moment. So the first software developed for SEM analysis was LeastRel. It is still active in use, but I can't say that I've seen many papers employing LeastRel. The second one, which definitely should be mentioned, is AMOS. AMOS is, let's say, an addition or add-on to SPSS, which allows easy plotting of SEM models, and for someone who is not so into let's say coding, programming, and for someone who is, let's say, doing a SEM analysis for the first time, AMOS is a good solution, especially because it is point and click. Here, just a small note, AMOS allows us to do just the covariance-based SEM analysis. So, of course, the analysis can be done in M+, can be done in R, using one of the most commonly used packages is the Lavaan package, which we will be using. Another software which is pretty handy is the Smart PLS. It is also a point-and-click SEM software, but it is pretty good in my opinion, because it allows you to do both parametric and non-parametric SEM, so covariance-based and partial least square SEM models in one software. Why is it also good? It's good because it also can do a lot of pre-tests in just one software. So usually if you're using AMOS, there are some analysis which you need to do, for example, in SPSS or in another software. But you're looking for a point-and-click solution to doing SEM analysis and doing everything in one software, I think Smart PLS is a good solution. Also, the analysis can of course be done in Python using the SEMOPI package. So as you can see, definitely there is a lot of options when it comes to software for conducting SEM analysis. So something we're also going to mention a little bit later is how to choose an adequate software, and is every software suitable for a particular SEM model which you are assessing. Okay, so when it comes to SEM in fact is a group of several analyses which are done under the same umbrella. So those analyses are path analysis, confirmatory factor analysis, and SEM models. So the only the difference between all these three, let's say sub analysis, is the type of variables the analysis is done on. So when we're observing the path analysis, we're observing the relationships between only measured variables. So we are just observing the relationship between the variables which we have in our data set. Confirmatory factor analysis is conducted when we observe only latent variables. So we are only observing latent variables and their correlational relationships. We'll see that in a minute. And a SEM model is, let's say, a combination of everything. So in a SEM model, we have latent variables, relationship between them, measured variables. So SEM model, let's say, takes into account both types of variables. So this is a pretty nice graph which I found, which in fact gives us graphically all the analyses which come under the umbrella of SEM. So now to what we will be talking today are, let's say, these three. So path analysis, factor analysis, and structural regression. So when it comes to path analysis, our idea is to explore the relationship between our measured variables. So whether we are observing path analysis, confirmatory factor analysis, or SEM analysis, more or less these steps are the same. So the first step is to draw a path diagram according to the theory. So what is characteristics for a SEM model and SEM analysis is that based on your detailed literature review, you devise a model which you are testing. So the first part is to create a diagram to graphically represent the relationship between your measured variables, latent variables, how are your measured variables going to be grouped, and so on. The second step is to conduct, as we said, regression analysis and to estimate the regression coefficients between your variables. The third part is to assess the model itself and to assess the regression coefficients. So we will mention that maybe a bit later as well. So whether you should leave all your variables in the model if they are not statistically significant, or maybe if they are statistically significant, but the values of your estimated coefficients are, for example, really close to zero, whether you should remove them from the model or keep them in the model. As we said, our fourth step is, if needed, you are allowed to make modifications to your model. Remove a certain measured variable, maybe remove a certain relationship between latent variables, and so and so on. So you can, of course, redo then steps 2 and 3 all the way up until you get a model which is of satisfactory quality. So when it comes to path analysis, there are some, let's say, assumptions that your data is continuous, normally distributed. And there is an assumption related to the number of observations. So your sample size. So some suggestions, some literature suggests you should have at least 10 observations per each your independent variable in the model. Some are more restrictive, and for example, as here on the slide, indicate the number 30, but literature these days is more relaxed and suggests having 10 observations per each independent or variable in your model. When it comes to drawing your model, there is also one more thing to have in mind. That is the type of dependency between your variables. So the dependency can be unidirectional. So based on your literature review, your ideas, and so on, you have an idea which variable is the dependent one, which is the independent one, and you know the straight the direction of the relationship. So that is one type of relationship which I usually recommend using in SEM models. On the other side, your relationship can be correlational. So you use this other type of relationship when you are not 100% sure which variable is the dependent one, which is the independent one. So based on the dependency which you assume and which you are interested in exploring, you will be using different, let's say, signage of the relationship tested. So here we're going to go through a pretty small path analysis model, just to, let's say, practice and maybe explain all the elements in the model, as well as the relationships which can occur in the model itself. So this is a pretty simple model. We can see that all of our 4 variables are in squares. So we know that all of these are measured variables found in our data set. So definitely here we are observing a path analysis model. What else? The model is such that we want to see how age, professional qualifications, and motivation impact our task. We also want to see how professional qualifications impact motivation. And what we have here is a two-sided relationship, the correlational relationship between age and professional qualifications. So in this model, it's a path model. All variables are measured. We have directional relationships as well as one correlational relationship. So what makes path analysis stand out from and SEM analysis from other analysis is that it allows us to explore both the directional and the indirectional effect between our variables. So definitely there is a directional effect between age, professional qualifications, and motivation on our task. That is something visible. But at the same time, SEM analysis allows us to explore the indirectional effect of professional qualifications through motivation on our task. So sometimes when we are creating a SEM model, we were, of course, observing the directional effects, but sometimes we can also delve a little bit deeper and observe the indirectional effect as well. Another thing which we should also observe here are our dependent and independent variables. So for each of our dependent variables, we will, as an output, obtain an equation. So what we can see first is that age, professional qualifications, and motivation are our independent variables. As we said, they are having an impact on our task. But at the same time, we should be aware that our variable motivation is a dependent variable in the model of observing the effect of professional qualifications on motivation. So as we can see, in a particular SEM model, a variable, latent or measured, can be in the same time a dependent variable and an independent variable, depending on the model and the relationship we are observing. So here, as an output, we would have two regressional models. So first would be the model related to task, where we are observing how age, professional qualifications, and motivation have an impact on task. And on the other side, we have a smaller model observing the effect of professional qualifications on motivation. So this is also something which makes SEM analysis stand out from, let's say, regular linear regression analysis. So what is the output of our SEM analysis? Well, it's nothing else than regression coefficients. So our main output from the model itself are going to be the regression coefficients, telling us how a certain independent variable impacts our dependent variable. So if we are having a directional relationship, such as here, so our output is the regression coefficient. If we are having a correlational relationship, such as here, our output is going to be a coefficient of correlation. So when it comes to our regression coefficients, they can be standardized or unstandardized. So when it comes to presenting the results of SEM analysis, in a way, it's up to you whether you're going to present the unstandardized or the standardized coefficients. Usually, reviewers ask to present both standardized and unstandardized coefficients. So definitely, I think it's completely fine to present both standardized and unstandardized coefficients in your results table. Okay, how does this sound for now? Do you maybe have any questions so far? Okay. So if there are no questions, then we can slowly continue. So before we talk about confirmatory factor analysis, first we're going to talk about the exploratory factor analysis. So when it comes to exploratory factor analysis, we as researchers or data analysts, we don't have an idea, we don't have a clue. How do we want our variables to be grouped? So for example, here in this example, we have 6 measured variables. We can see they are marked in squares, and we want them to be grouped into latent variables. So as we can see, each variable is connected to each latent variable, meaning then that after conducting the analysis, a situation could have been that variables from x1 to x5, all of them are in latent variable 1, and that variable x6 is in the latent variable 2. So When it comes to exploratory factor analysis, we have no power on deciding how our variables are going to be grouped. So exploratory factor analysis tells us how our variables should be grouped. On the other side, when we are conducting confirmatory factor analysis, which is a part of SEM, we as data analysts, let's say decision makers, we already in advance know how do we want our variables to be grouped. So for example, here, we know and we want to group x1, x2, and x3 in latent variable 1. So for example, this is a particular scale that we know it is a scale. We want these three variables to be grouped. And on the other hand, we know that x4, 5, and 6 are another scale measuring another phenomenon, and we want them to be grouped in latent variable 2. As we said, the relationships within confirmatory factor analysis are correlational. So as an output, we will receive a coefficient of correlation between our two latent variables. So exploratory factor analysis, we have no power on how our variables are going to be grouped. In the confirmatory factor analysis, we are the main decision makers and we have, let's say, the power to decide how our variables are going to be grouped. Okay. Okay. So after CFA model, we can also see an example of a SEM model. So this would be a SEM model. Why? Because in this model we have both measured variables, we have latent variables, we have relationships between them, and our relationships are directional. So for example, this is an example of a SEM model which we created for a study on leadership. For example, here we wanted to explore how different types of leadership do they have an impact on different types of organization of outcomes. So, for example, each of these, let's say, these outcomes have been measured using different measured variables. Okay, so based on our literature review, based on the data we have collected, based on our hypothesized model, which we created, now we have a model, whether it's a path model, whether it's a confirmatory factor analysis, or a more, let's say, complex SEM model, there is another question for us. So another question is, which type of algorithm are we going to use to estimate the regression coefficient? So should we use a covariance-based SEM analysis or partial least squares SEM analysis? So this slide and this table should help us find differences between the two algorithms, and based on our model, our data that we are dealing with, can help us decide and choose which algorithm to use to assess our model. So when it comes to type of data, if you are dealing with scale data, so like height, weight, some particular measurements, or even data on a Likert scale from 1 to 5, and then if you have a large model, you can use covariance-based SEM. But if you need to add certain nominal or ordinal variables in your model, you cannot use a covariance-based SEM. You would need to use the partial least squares SEM algorithm. So this is, let's say, first thing. So based on how your model looks like and which type of data is in your model, you you choose the algorithm, the estimation algorithm. So when it comes to some distributional assumptions, covariance-based SEM is in fact like a parametric test. So its assumption is that your data is normally distributed. On the other hand, PLS-SEM is like a non-parametric model, meaning that there are no assumptions on the distribution itself. If we observe just these two, let's say, characteristics of comparison, it is pretty clear that non-parametric SEM is more maybe used than covariance-based SEM, especially that it can be used on the different types of data. The second thing one should have in mind is the purpose of your model. So if you are devising a model and you want just to test the model, whether your model stands or no, covariance-based SEM is more trustworthy in that sense. But if you want to generate a model which will be later used for some predictions, then PLS-SEM is a better solution. The second characteristics is related to hypothesis testing. So if we go back to linear regression, we said that each of our coefficients can be tested, and there is a statistical test to tell us whether a particular coefficient is statistically significant or no. So if you're using a covariance-based SEM, there in your output, there will be a table with value of the statistics and p-value, which will help you decide and make a conclusion whether a particular coefficient is statistically significant or no. However, when it comes to PLS-SEM, no such table is available. In order to test the significance of a particular coefficient, bootstrapping has to be conducted. Next characteristics is the sample size. So covariance-based SEM requires a large sample, while PLS-SEM can work with pretty small samples. So if your population is small, your sample is small, it's maybe better to do analysis using PLS-SEM than using covariance-based SEM. When it comes to missing data, covariance-based SEM doesn't allow missing data, PLS-SEM does. When it comes to statistical power, covariance-based SEM has higher power. And another interesting difference between the two is the type of relations which can be modeled. So when it comes to covariance-based SEM, you can only make reflective relations. When it comes to PLS-SEM, you can make both reflective and formative relations. So let's see what is the difference between reflective and formative relations. So the main question here, which you as somebody who is creating a model should ask yourself, are your indicators causing or being caused by the latent variable construct measured by them? So we can see that there is a difference between the two. So in one, on the left part of the slide, we have a particular construct which has an impact on certain indicators. So changes in the latent variable directly cause changes in the assigned indicators. On the other hand, there is another situation where our indicators have an impact on our latent variable. So changes in one or more of the indicators causes changes in the latent variable. So depending on the direction of our relationships, we have reflective and formative models. So both of these models can be created and can be assessed using PLS-SEM. So here is maybe to make a better distinction between reflective and formative models. So, for example, if we have a reflective model, we have our latent variable drunkenness, which impacts that we can't walk in a straight line, we smell an alcohol, and we are not able to speak very well. On the other side, formative is the type of relationship where our measured variables have an impact on our latent variables. So in a formative model, we would be observing how consumption of beer, consumption of wine, consumption of liquor have an impact on our drunkenness. So this is also what one should have in mind, that the different approaches to creating latent variables can be taken. Okay. How does this look for now, and are there maybe some questions? So when we made a comparison between the two, there are also yep. Thank you for the comment. Okay, so after we let's say saw some differences between the two types of algorithms, let's see how we can estimate our SEM models. There's a long list of different indicators, metrics we can use. So here on this slide we have a list of just a couple of them. So being a parametric SEM, there are a lot of metrics we can use. So some of the most commonly presented ones are the chi-square test, or the value of our chi-square statistics. So the lower the value of our chi-square statistics is, the data better suits our model. So our goal is to have the lowest possible value of chi-square statistics. So another one is root mean square error of approximation, which should be below 0.1, as well as a couple of indices like comparative fit index, CFI, or Tucker-Lewis index, TLI. So all of these indices, they are observing the difference between your data and your model, and they're just observing those discrepancies from different angles and perspectives. So for them, it's just important to know the threshold, how to comment on the obtained values of the indices. So, for example, CFI, TLI, they should be above 0.9. So, for example, in this paper, they really nicely presented some of the metrics you can present, as well as the general acceptance rule. But what is maybe a problem? A problem here is that there is no particular guidelines which of these indicators you should be presenting. So in sense, it's a little bit up to you as an analyst to choose which of the indices you will be presenting. But as I said, some of indices are common to present, or so those are value of the chi-square statistics, RMSEA, as well as NFI and CFI. But of course, I mean, if you want, you can present others as well. When it comes to validation of PLS-SEM models, as you can see on the slide, there is visibly less metrics which can be used. So most of these, the first three metrics are more used to assess each construct than to assess the model itself. So what can additionally be used, of course, is the coefficient of determination. Coefficient of determination can be used for both covariance-based and partially square SEM models. But as I said, when it comes to PLS-SEM models and the model quality, construct reliability, convergent validity, and discriminant validity are most commonly presented. Okay, so definitely there are advantages and disadvantages of SEM as of each statistical method. So an advantage is that it's a graphical analysis. It's based on two widely acknowledged statistical methods. There is a lot of software available for its construction. It can be applied in different fields of study, and is pretty commonly used to verify certain conceptual models. But of course, there are disadvantages. So definitely you, as somebody who is conducting the analysis, should be pretty careful. As we said, the analysis has to be redone quite a number of times. So sometimes you as an analyst can play a little bit too much with your data and get a perfect, let's say a perfect fit. Sometimes models can be very complex for presentation, interpretation, and so on. So one should be careful on the complexity of the model itself. Usually a large model is needed, especially if you want to do a covariance-based SEM. So at least 200 respondents is needed for a model of, let's say, medium complexity. Another thing which occur are, of course, some issues. And for example, on this slide, I listed some of the questions which I, let's say, encountered which I encounter almost every time when creating and assessing a SEM model. So the first question is which SEM software to use. So if maybe it's your first time doing SEM analysis and you will be, I would suggest Smart PLS, and as it is, let's say, an omnibus software for SEM now. In one software you can do the covariance-based SEM, partially square SEM, as well as a number of pre-tests usually needed to do SEM analysis. But again, if you have a particular model in which you have nominal variables, ordinal variables, then I would definitely suggest using R or Python, because specific algorithms made for ordinal and nominal variables are implemented in those softwares. So those algorithms are still not part of, let's say, Amos or Smart PLS. The second question is how complex a model should be. So that definitely depends on your population or on your sample size. So if you have a very complex model and the very small samples, sometimes even, then it's maybe better to remove some latent variables from your model, or maybe use averages of scales or latent variables as a replacement. How large sample is needed to evaluate the created model? I would always say the larger model, the better. So of course, if you have a small sample, Smart PLS can come as PLS-SEM can come as a solution to that. But of course, if you have quite a small population, you're going to have a small sample. So in that sense, your hands are tight. So again, the larger the sample, the more sure you are that your estimates are going to be good. Fourth question is related to pre-tests. So we'll talk about that when we go to the practical part. So when conducting SEM analysis, there are certain pre-tests which would be done, which confirm that your variables, your measured variable, can be grouped into a latent variable. So Cronbach alpha is usually presented, but besides Cronbach alpha, we can present average variance extracted or CR. So there are other measures of internal consistency and validity which can be presented. Should we leave in the model or not those relationships that are not statistically significant? So if there are some relationships which are not statistically significant, you can remove them from the model. Because removing non-significant relationships is not going to improve or make your model worse. So my suggestion is, if you're having a model of low complexity, you can leave all the relationships in the model. However, if you have a pretty complex model with a lot of lines on your graph, maybe it is easier to remove the non-significant relationships to just to improve the interpretability of your model. So is it possible to form latent variables from latent variables? So yes, something like that is possible. It's called hierarchical SEM modeling. If you want to try having latent variables made of latent variables, completely fine. Just have in mind that for such an analysis, you would need a large sample. And the seventh question is, should the regression coefficients that are weak be kept in the model? So one part of the literature suggests that every regression coefficient which is below 0.5 should be removed. So in that sense, it's again, it's up to you. If the goal of your model is to try and find as many predictors as possible, you will not be deleting any relationships. But if you just want to find the relationships which are strong, then you can of course delete statistically significant regressions. From my point of view, I don't support deleting or erasing the relationships which are statistically significant, because depending on the field in which you are creating your model, the relationship, the value of your coefficient depends. So, for example, if you're creating a regression coefficient on, let's say, consumer behavior in marketing and trying to find out what are the predictors of whether a person is going to watch a movie or no, I mean, from one side, it's completely fine to have coefficients, regression coefficients, which are pretty low, because there are so many factors impacting your dependent variable. It's not realistic to have such strong relationships. Again, this also depends on the model and on the field in which you are creating your model. So with this slide and this, let's say, long story on the issues which can occur in a SEM model, I'm finishing, let's say, the theoretical part on the SEM and different approaches to estimating a SEM model. So if there are no questions, I suggest that we maybe make let's say, a small 10 to 15 minutes break before we go back and see how we conduct both covariance-based and partial least square SEM in R. Okay, so if there are no questions, I suggest we make, let's say, 15 minute, 10, let's say 10 minutes, 10 minutes break. Thank you. Okay, hello everyone. We're back, let's say, after our short break. So let's go back and continue with our tutorial. So after let's say talking about some of the issues which can occur when creating and exploring a SEM model, let's see how we actually assess a model in R. So as our example, I gave you a small data set related to an actual research conducted a couple of years ago on the topic of marketing and sport sponsorship and the sponsorship within the UEFA Champions League. So in our data set, we have quite it's a small data set in which we have, let's say, three latent constructs to explore. Those are involvement, exposure, and attitude. So involvement as a construct has the goal to measure how much a person is involved in football as a sport. So we can see that within that latent variable, we have four questions, four measured variables, all of them which are measured on a 1 to 5 Likert scale. The second one is exposure, where we were interested in measuring how much a person is actually watching the UEFA Champions League. Again, we have four statements. And finally, we have attitude, where we explored the attitude of a person related to the sponsors of the UEFA Champions League, where we had three measured variables. So the first thing when talking about SEM in R is the R syntax. So when we are creating a latent variable, so on the left side we have to give a name to our latent variable. Then as a sign that it is a latent variable, we're telling how our latent variable is created. So we are using the sign equal and tilde, and we are listing all our measured variables. By default, we are putting a sign plus between our measured variables, and of course that sign can be plus or can be minus depending on our model and our data. If when we are observing the regressions between our latent variables or measured variables, so on our left-hand side is our dependent variable, so with the one we want to model. On the right side are our independent variables, and to assign that it's regression, we are using the tilde sign. If we have residual correlations, if we want to correlate the measurement errors, if you remember back at the beginning, we said that in SEM, each measured variable can have a measurement error. So we can make correlations between those errors to improve the quality of our model. So if we are making those correlations between the errors, we are using the two tilde signs. So the model which we will be creating is the model where we want to see how involvement impacts exposure. So involvement will be made from variables E1 to E4, exposure with variables E1 to E4, and we are observing the relationship between the two latent variables. So it's a pretty simple model, but it will work for us. Okay, so the data set I've provided you is SPSS data file. So in order to read an SPSS data file, we need to call the package foreign, within which we can find the function opening SPSS files. So let's call our data our matrix football. The function we need to read our SPSS file is read.spss. The parameters of our function are, let's say, where our data set is stored, and additional are two parameters related to whether whether we want to use the labels of from our data set or no. Using the function str, we can just see the structure of our data. As we can see, our data is measured on a 5-point Likert scale. We can see that in our data set, we have 444 observations, so that is the number of our respondents, and we have 8 variables in our data set. So, as we said, prior to conducting a SEM analysis, there is a need to do scale reliability. We need to see whether we can actually group our variables in a latent variable. So to measure scale consistency, most commonly Cronbach alpha is used. So Cronbach alpha is a matrix which takes values between 0 and 1. The closer it is to 1, the more our scale is consistent, meaning that the questions within a particular latent variable are in fact measuring a particular phenomenon which we are interested in. So here we need to know the threshold for the Cronbach alpha. So the threshold for Cronbach alpha is 0.7. So if we have a Cronbach alpha above 0.7, we are in a way sure that our variables are measuring the same underlying phenomenon. Everything above 0.7 is considered fine. However, one should have in mind that Cronbach alpha can be sensitive to the number of measured variables within a scale or within a latent construct. So sometimes if you have maybe 2 or 3 variables, sometimes you can get a smaller Cronbach alpha, even though those variables are in fact measuring the same phenomenon. So, but nevertheless, so values above 0.7 are considered good. So. First, let's explore the Cronbach alpha, and let's see whether we can actually group our variables 4 by 4. So how are we going to do it? So first we have to create subsets for each and every construct. So we have our first construct, call it C1, our second construct, C2. To get our Cronbach alpha, we need to install and call the package psych. The function for calculating Cronbach alpha is pretty straightforward. It is just alpha, where the parameter is the subset on which we want to calculate our Cronbach alpha. So, for example, if we are calling Cronbach alpha for the first latent variable, which is here would be our results. So, as you can see, R produces quite a number of results. So let's go one by one and see how do we interpret them. So rho alpha is the measured Cronbach's alpha. So for our latent variable involvement, the measured Cronbach alpha is 0.9, which is definitely above 0.7, and we are sure that we can group our variables into one latent construct. So in the line below, what we can find is the 95% confidence interval for our Cronbach's alpha. So sometimes you can be interested in presenting the confidence interval as well. So what is also pretty nice, what R presents you is what if analysis. So what if analysis in fact tells you what will be the value of Cronbach alpha if a particular variable is removed from the construct. So the first line is in fact related to what would be the Cronbach's alpha if we remove the variable I1. So if we remove I1, our Cronbach alpha is going to be 0.9, so no changes. If we remove variable E2, our Cronbach alpha is going to be 0.86, which is a decrease, not something we want. The same would happen for E4 and for I3 and for I4. So what if analysis, in fact, can help you and tell you, are there some variables which you can remove from your latent construct to have a better internal consistency? So for example, here, there is no need to remove any variable from this construct. The same analysis can be, of course, done for the second latent construct. But usually, when doing a SEM analysis, so the first step would be Cronbach's alpha and presenting the rho alpha per construct, as well as the number of items or questions within the latent construct. So, as we said, Cronbach alpha is sensitive to the number of measured variables within a construct. So next, let's go to the application of the covariance-based SEM in R. So we will be using three packages: Lavan for model assessment, SEM tools as well for additional model assessments, and SEM plot to plot our model. So when it comes to creating and estimating models, SEM models in R, there are several steps. So the first step is, in fact, to create the model itself. So with this analysis, with this code, we are just creating the model. So for now, we are just telling R, how do we want our variables to be grouped, and what are the relationships between the variables we are interested in. So let's call this a SEM model, and within each line we are writing the equation for each latent variable. So involvement is going to be made from variables I1 to I4. Exposure will be made from variables E1 to E4. And we want to see how involvement impacts our exposure. So with this, we are just creating a SEM model. So far, we have no results on the model fit, and our coefficients. So the next step is to actually estimate the model. So I always suggest creating an object with the results and the solutions. Here we can call it model.fit. You can call it however you want. So the function itself is pretty straightforward for now. It's just SEM. We're creating a SEM model. The two parameters are the model, which we previously defined, and the data set on which the model should be should be estimated. With this line of code, we're just conducting the analysis. There is no special output for this line of code. However, the function summary is going to provide us with detailed results. So we want summary of our model fit. And additionally, what we want to get our fit measures. So those will be all the model quality model coefficients which we mentioned, and we want that to be true. So the first interesting thing we can read from the output is the value of our chi-square statistics. So model fit test statistics is in fact the value of our chi-square statistics. We can see the degrees of freedom, and we can see the p-value for our chi-square statistics. So, for example, here we would say that in this model, the value of our chi-square statistics is 138.393, and we have a p-value which is less than 0.00001. So there is no special way to explain or to interpret the value of the chi-square statistics. We said we're interested in it being the lowest possible. So going down through the output, we have the analysis per construct and the analysis on the relationship between the constructs. So the first column, called estimate, are in fact our unstandardized coefficients. Our column z value is in fact the value of our statistics, and the p-value is in fact telling us whether a certain coefficient is statistically significant or no. Our null hypothesis states that the coefficient is not statistically significant, while the alternative one states that the coefficient is statistically significant. So, if we, for example, observe the structure of involvement, we can see that all measured variables are statistically significant. When it comes to exposure, one of them is not statistically significant. So maybe in some redoings of the model, we can consider maybe removing this variable from our latent construct. So what we can also see when it comes to creating latent constructs, here we have 4 variables, but we do not have 4 set values and 4 p-values. Why? Because the first variable, which we indicated that makes our latent construct, must be fixed and must be statistically significant. So for the first variable in our latent construct, its weight, its coefficient is fixed, and it is always statistically significant. If we look at our regressions, again, we can see that the relationship is statistically significant and it is positive. Also, what we said is that here we are given the unstandardized regression coefficients, and it would be interesting for us to find our standardized regression coefficients. We're going to see that a little bit later. If we continue scrolling down the detailed output R provides, we can find our fit indices. So, for example, here we can see that both CFI and TLI, the 2 indices, are above 0.9, telling us that our model is of pretty good quality. However, we can see that our RMSEA is a little bit above the 0.9 threshold, but as that difference is not that high, we can say that the model is of fine quality, taking into account the RMSE. So if we want to get our standardized regression coefficients, which are maybe easier to communicate, we have to use the standardized solution function, where the parameter type is standardized all. So again, we will be having the set values, p values, but we will be having as well the standardized coefficients. So as we said, you can present just the standardized, just the unstandardized. It's up to you when it comes to that aspect. Okay. Thank you for the acknowledgement that we have let's say a couple of more minutes. Then I'm just going to go. This is related to the drawing of the SEM model. That is something you can also look in the presentation itself. When it comes to PLS SEM in R, we will be needing an additional package, SEM PLS. Here the idea is to have, let's say, a smaller sample. As we said, the PLS-SEM is done on smaller samples, so we are going to create a sub matrix of just the first 150 respondents. Here, the algorithm and the code itself requires making submatrices. So we will have to make a small submatrix for each latent variable in the model. As you can see, the syntax for creating our latent variables is way more complex than it was in covariance-based modeling. So first we have to make the measurement model to define our latent variables, and then to create a model to define our structural model, or the relationship between our latent variables. So more or less, this part is the same. We first have to create our model, tell what is the structural model, what is the measurement model, and then we estimate the model itself. We have to tell what is the model we are estimating, what is the data we are using. Again, we will be receiving as an output, we will be receiving coefficients. The greater coefficient indicates within which construct a variable will be allocated. So we can see that the first 4 are in the involvement, the second 4 are in the exposure, so everything is fine. Here is our path coefficient. As you can see, we just obtained a path coefficient without its significance level. To obtain its significance level, we have to do bootstrapping. So if you are interested in conducting and trying smart PLS, here would be the code. So bootstrapping here is set to 500 replications. So we will make 500 subsamples, estimate the model on them, create the statistics, and based on that, we explore whether our coefficient is statistically significant or no. We get our estimates, we have our intervals, and based on that, we can make a decision whether a certain coefficient is statistically significant or no. So this would be, let's say, a short recap on what we've done. We saw some advantages and disadvantages and some characteristics of both covariance-based and partial least squares SEM. So definitely based on your sample size, based on your complexity model, based on your variables, you will have to choose which of the two algorithms you will be using. So in order to keep up with the time, maybe a faster ending. But again, I'm here for all the questions. You have my email, so if you have any questions, please feel free to contact me. Thank you for everything.
Thank you so much, Milica. The tutorial was full of useful information and it was genuinely interesting. And thanks everyone for watching the tutorial.